So at torsion, okay, we are going to focus on observing the. This is basically an example of how we could consider a torsion or torque that has. We consider the wrench when you are looking at the car, the tires on the car. When we put the wrench and try to rotate, basically we are giving some forces that is going through this member. Okay? This member. Okay? So that member will be a torsion member. We say this is a torsion member. Okay? So with a magnitude of P, okay. So you see that P is going down on point A and P is going up on point E, right? And it has some distance, BC and BD. It has some distance B. Okay. So the shaft will be the torsion member. Okay. And I think this is very good example. And if we see the shaft AB, we take a look into more clear and we cut AB from this structure, we see that we have some torque on this particular members, okay? And then we can distribute the shear stress inside the member. So when you take the torsion, when you give some torque power, for example, we take a okay, so if we take, for example, this is a rod, we take this, okay, you see that this line is getting twisted, right? Now, that is basically what we are going to observe. When we twist this, aside from the forces that is going to be distributed inside the rod, if we see how the line, the blue line here, it's going to be twisted, right? The twisted means, if you remember what we have learned before, the shear strain, it has some certain angles, right? And that angle also will incorporate in this torsion. And that is one way to, so one section on this torsion is going to find out how much the angle will be twisted. Okay? The twisted angle, we say twisted angle, but that will be for the, after these introductions. Okay? And then if we see the inside, and if we see the bulk of the rod, if we give the torque, then inside of this rod, there will be ongoing shear stress on every members of the rod. Okay? There will be a shear stress that is going inside, the internal shear stress. Okay? And that is also important to give an analysis. And the basis, okay, the best way to look this torsion, if we want to compare with the previous chapter, we can have some analogy. Okay? So in the previous analogy, we have the axial force, right? In the longitudinal axis. And in torsion, we focus on the torque, okay? The torsion. Okay? The previous one, we see the elongations. But now we are going to see how the angle will change, how it's going to be twisted. Okay? We see the normal stress before, and now we are going to focus on the shear stress. Okay? We see the extensional strain, we see the shear strain, the angle, right? We see the modulus of elasticity, and now we are going to see the shear modulus. Okay? So it's quite, we can say that it's like a counterparts for each other. And I think basically it can give you an idea on how we are going to see or observe the problems in the future. So we are going to see torque, twist angle, shear stress, shear strain, and the shear modulus. Okay. Okay. So these 5 points, that is going to be a counterpart for each one of them. Okay. Okay, and now if we look at how the examples of the so there is a 2 picture actually, rod and the bar. Okay. So the first one is the rod. You will see it's going to be similar what what we have done in my my rod here, right? And the second picture is bar, okay? And you will see that it's going to be twisted here. This is the sides of the bar, okay? So that's the example of torsional deformations. Okay. Now, one thing that is going to be you need to be one takeaway from this example is if we look at the circular shaft, okay, so circular shaft, let me write here, whether it's solid or hollow or tubular, when subjected with torsion, each cross section remains plane. And simply rotates about the axis of the member. You can see when we compare these 2 pictures, okay? You see the first picture it seems that it's still the same circle, right? The whole thing is the same circle, but the difference is this the line here that previously a straight line has become twisted, right? But the cross section, if you cut, still circle, right? Still circle. But here they are, for every section there's change, right? So for Shapeless shaft, we can see that it remains a plane, and for most of the part, we are going to deal with this rod. So if we want to, let's say, take some small points, okay, we can see how before and after deformation on those small points. Let's check here. Okay. So this is a circular cylinder from point A, B, C, D. And let's say we are going to have a twist. Okay, we have a twist, we have a torque with a magnitude of P, this torsion here. Okay. And you will see that this A, B, C, D will have a new set of points that is going to denote that they are twisting, okay, they are twisted. And you will see that it has some certain angle that changed from the previous original source. Okay, it's stated that this is with the side L, or this twisted angle. We say this is the twisted angle. And of course, if we look on the ABCD at the beginning, the ABCD has a right angle, right? Each of them has a right angle. It's like a rectangular shape. But now the right angle is changing. Okay, this is because there are shear forces that is going inside, right? Shear forces or shear deformation. Angle change on ABCD. Okay, now before we move on, let me write some assumption or fundamental principle. Assumptions on torsional deformation. Axis remains straight. Okay. So the core axis is still on the same line, okay? And it's remain inextensible. So it's not going to increase, okay? Axis is still straight. We'll write again, every cross section remains plane and perpendicular to the axis. And 3, radial lines remain straight as cross section rotates about the axis. I think this assumption is quite understandable. If we make the axis have another deformation that makes the axis elongated, then our mathematical model will be very complex and difficult to write down. So we want to focus here. All the things that's being done is just being done by the torsion. Okay? So we are going to focus on torsion. Okay, now our goal is actually, because we know that from previous sections, we know that there are shear strain, right? And now we have this twisted angle or the torsion deformation, this phi L. Then we are going to connect this twisted angle with this the shear strain, how to connect mathematically. So at the field section at the beginning for the torsions, as usual, I will mention more concept on related to limit calculus and so on and so forth. But in practicality, we are going to see that in exercise we can do directly to the direct formula for the torsion itself. But I need to start with this concept first to get to so that we are on the same page on the basis. Okay. Okay. Now see this first. See this conventions here. Let me just make smaller a little bit. So we are going to see an example here for torsional deformations. Okay. It's a little bit complex, but we are going to see that since this is the twisted line, right? And let's say we are going to make a sample from this middle point here. Okay? So this middle point, we are going to see the change in D. Okay, so this is the original D, and then it's twisted to be this D with asterisk, okay? The new D. Now we are going to see how much does it twist it. Okay? How big the angle. Okay? This is the angle, right? The angle. Okay? And let's say we are going to take the angle as a sample with a variable x. Okay? Let's say we have this a function, the phi of x. Okay? And let's say this is going to be a small delta x. And if remember, if we deal with the small delta here, then practically we are going to deal with calculus. Okay? So we are going to see and observe how this particular angle will be written down mathematically, and we are going to connect those with the shear strain later. We look here at the end of the this f and change to f asterisk. This is when the functions or the x is L. Okay, so we say this is the final angle at this point here. Okay, right? The phi L will be. Okay. And now to make the convention or the sign, you can use your right hand. Okay, to give you an idea how this is going to connect. Okay. And this also going to connect there, your right hand. This is for the internal torque. Okay. So if we cut open. If one side have this torque, then the other side must have another torque, okay, that resists the torsion in general. Okay. So our goal now, relate the shear strain and the angle or the twisted angle okay, that's our idea. Now to relate the shear strain, then let's say we are going to observe the element of the small delta. Okay, let's say this is our element. So we put away and we are going to zoom in. And let me maybe write a little bit here. Okay. So let's say this is an element for the delta x. Okay. So it's a little bit complicated, but the focus for our observations is look on the new point, the R, okay, the S, okay, and later on is the, but let's say this first, okay, let's say the R and S. The R have the new R here, R asterisk, S have S asterisk, okay, and within the delta x length, and if we say that this is x, then the other part will be the additional of the delta. Okay? Or if we say in the functions the phi x plus delta x. This is the angle, okay? And this is the radius, okay? The radius, the inside radius, and this is the radius for the rod. So let's say this is this rho is the concentrated radius in the core, okay, core, central core of radius. And now if we focus on the core of the radius, okay, so we just see only in the inside, the inner core, then this is the core, okay, the core of the radius rho. So we are going to see the inside. Now we have Q, another Q here. So R, Q, and this RQ is going to change into new positions, the R asterisk and Q asterisk here. And then the S, as we mentioned before, is becoming the S asterisk, okay? And then we have this S prime, okay? The S prime. So if we see from the previous one here, let me write first, the angle of QRS is right angle. And then as a result of deformations, the angle is now changed to angle that is the new position. And this will be smaller by the shear strain angle, or this angle here. So to know this strain angle, we take a line from the first, or the original, or the first line here, take a line parallel to the original line here, so parallel to this, and we name this point S prime, okay? Okay, if you remember this shear strain, if we take the functions x and rho, this will be pi over 2 minus that angle, right? The angle of the Q, R, and then S, okay? Remember that at the beginning we have the right angle, and we can think like a rectangular, and then we shift it, right? We twist it, and it's becoming lower than the right angle. Okay? How low they are going to be, the angle will be, is based on this angle, the new one here. Okay? The new one here. And this will be equal to the angle of S prime, R, and then S asterisk. Practically saying that that is the one strain, the shear strain that is going to be observed. Okay? And then remember that because the angle is very small, Okay. So right here, since this shear strain is very small, so the sine and the tangent, they will be equal, or not equal, will be very close. The value will be very close. So we can approximate using tangent. Because basically, if you see like a triangle, if this is a triangle, then we can take this angle and then compare with this length and this length to make a tangent, right? To make a tangent. So, and then at the same time we take the limit. Okay, so we take the limit as delta x getting close to 0, or as we cut the sample very, very small. Okay, then the tangent, or we say the s asterisk s prime, that's the let me write here. It's going to be like this. Okay, so the tangent, right? The tangent right? So we can write also here. So the tangent is equal to its angle itself. And now we can take that the distance, the s prime, if we take, so remember, this is the arc, right? The arc of the circle. This is the sector. So we can take this and say this will be equal to rho multiplied with the delta, right? So we can take this as a limit. This is rho delta phi over delta x. Or we could say, in terms of derivative, then we can take the limit, and we are going to have rho d phi dx. This is from, let me give you some help here. This is s prime, s, that prime, right? And we have here, this is rho, and here we have delta phi. Okay? And we know that the s prime s asterisk is rho delta phi. So we call this the strain. Let me write as a conclusion here. The strain is equal rho d phi over dx. This is called the strain displacement equation. So the strain, this is shear strain. Let me write here with some explanation. This is shear strain at cross section x at a distance rho from the axis, and this derivative, this d dx of phi is the twist rate. You can think the twist rate, if we think like in the calculus, this is d dx of the phi. Okay. So how fast the twist or how fast the angle will change. You can say that. Now, based on this formulation, the shear strain displacement equation, then we can say if we have a bulk rod, then we can think like the more we have if we compare the distance like from the inside the inner core and maybe a little bit outside and until the outer side of the rod, we can predict how the distribution of the shear if we could take into in more details here. So if we take, for example, here, we can see that we can take this strain max, okay, this shear strain max. For example, the left part is just the same, the bulk rod, but if we have the, let's say we have something inside here, still the strain max is taking the outside here, the outside, the radius outside. We are going to see how we are going to observe it more clearly this figure, okay, with a more another assumption that is going to be linear elastic circular bars. So we see the deformation, and after this section, we are going to see the stress, okay, the shear stress. Okay. So if we take a look at this graph, let me put this side here. Okay. So if you see the torsional deformations, so from A, B, C, D, the picture here, if we are going to imagine how the shear stress will be, so if we first, let's say the A and B, so we cut this rod, and we are going to see um, the internal forces. So there will be, inside this rod, of course, there will be an area that is affected by this torsion. And how they are going to be affected, if we're going to zoom in into each part of this small sample here, that in each sample, we are going to see that they are all going to have this shear stress. Okay? At every element they will be having a shear stress. Okay? So every element they will be having a shear stress here, okay? And shear stress here. Okay? So there will be the shear stress that is not only on the cross sections, but there will be always shear stress that is on the radial planes. And we can take this small sample here and take the sum and then take the integrations, and we are going to get this resultant torque. Okay. So basically the torque will be force and the distance, right? Force and distance. Well, in our case here, our distance will always be the radius, okay? Because if we see from the cross sections, that radius will be very, very crucial to determine how the magnitude of the torque will be. Okay? And then the force, of course, the force that is acted on this part is going to be the shear force, right? The shear force. Or if we want to make the force going to be in element, we are going to see that this is going to be the shear stress and the area. And the area is the part that we are going to see small part in the picture. So we are going to take the integrations, rho tau dA, and integrate with respect to A here. And of course, in the area here, you should remember what will be the dA. This is r, dr, d theta. Mean calculus. Or will be it's already evaporated. Okay, because the area, the cross section area is the circle. Okay. Okay, now if we look on more clearly here. So this is the element that is going to be in the integrations. Okay. So this is a small element. Okay. The small element is a part of the circle, right? The circle. So the circle, if you remember, if we throw on the polar, we need to have the radius and the angle, right? For the dA. And then that is the F, this one, the resultant force. That is going to be the shear stress and dA. Okay, so we can say we can have the shear stress distributions, right? Along this radial plane. Okay. And then this is the resultant torque. So we can directly write integration of rho, tau, and dA for the torque. So that is the resultant torque. So we could just write down this. Okay. This is resultant torque. Oh, I think I already write. Oh yeah, already here. Okay. Okay. This is shear stress let me make the title shear stress due to torsion. I forgot to mention the title. So after we know the shear strain, the shear stress, and now we connect strain and stress, the first thing is we are going to assume the linear elastic, which means that we are going to see the modulus, okay, modulus of elasticity. In the previous axial forces, or in the previous chapter 2 and 3, we focus on E, right? And now we focus on G, the shear modulus. So let's say we're going to have, okay. So we are going to see the linear elastic stress strain behavior, okay? So we start with this. Well, let me start with in axial force, if you remember, in axial force we say stress is E and strain, like that, right? Now in torsion, so in torsion of circular bars, we say the shear stress is equal to G multiplied with the strain, the shear strain. So this is the Hooke's law for shear. And now we say the strain, we know from the previous calculations or mathematical models that this shear strain is equal to rho, and the twist rate, we have the dx of phi, the twist angle. Now we can write this shear stress as rho ddx of phi. Okay, so from the beginning of the lecture, the torsion, the introductions, we will start more concept, okay, that is related to calculus, limit, okay. But eventually, after we move on after several sections, we are going to see the more practical way, okay, because now we see more practical, right? Later than before, we see this sampling from the limit, right? But now we still have a problem, okay? We still have a problem of this rate, okay? Now, how to take this into next step, okay? The next step. So, first is we need some assumption, okay? If this is in the linear elastic, then perhaps one good assumption is, let's say we assume first the torsion bar is homogeneous. What does that mean? That means the G will be constant. So we can say the shear stress, the tau, will vary linearly with distance, the radius. So if we see this picture here, this is what does it mean. So we can see that the stress, the shear stress from this core shaft, if we take the distance, there will be changing linearly. Okay. Why linearly? Because we take this homogeneous bar. The G is a constant. And we can say that the maximum is on the outer side here, the radius when it's equal to rho, and when radius is equal to rho. Okay. So we say the GR d phi over dx. And of course, we can, if we take this two example here, we say we have two different radius, the inside radius and the outside radius. We can also say still the maximum is the GR, the phi over dx. But now the R is the R outside. Now this will be important because we are now going to define what will happen in the torsion equations. Okay. Okay, remember the torque. Let me see where it's here. Remember this is the torque, right? The torque equations. So the torque, let me write here, is equal rho, the tau, and the A. Okay. Now let's change the shear stress with this. Let's change with this. Change with that. Now the torsion integrations is G rho okay. And we know that G is constant, so we can take out G. And then d phi over dx we can also take out. That is the rate for the twist rate itself, not in our integration, because integration is just with the dA. So we can take integration of A rho squared dA. Now this is what we call, these integrations, this is what we call the polar moment inertia. Okay. Now we need to simplify this. So we need to simplify this by taking the inertia. Okay. Taking the inertia that we have already known before, supposedly, but let me just write the inertia. Okay. The inertia the polar moment inertia for a solid. Let me write first. This is the formulations. So for solid cross section of radius r, the inertia will be pi r with power of 4 over 2. Okay. And then for tubular shaft, it has outside radius and inside radius. The inertia is pi over 2, the outside minus the inside, both with the power of 4. Okay. In short, this torque we can write as the twist rate equal T over G and inertia. P is for polar, so inertia for polar, moment inertia of polar, or polar moment inertia. Okay. But still, it's not that practical, okay? Because we still have this rate, and sometimes we want to know the exact angle, right? Well, if you see how we develop this, and you can probably intuitively can predict what will be the formula if we want to know just the angle. We just move this x to here, right? So that's another way to see. Later we will go into this. Or we can also write, let me write around here. We can also write using the stress, the shear stress equal the torsion rho over the inertia. So by combining all the together, we can also write this shear stress formula. Okay. Now, giving you context for this shear stress and torsion, let's start to look at this example here. So we have a torsion bar, bimetallic, so which means that there will be two materials. So the shell is aluminum, and bonded to the outside of steel core. Aluminum shell bonded to the outside of a steel core. And we have both have the G, each of them, and the shaft has the dimensions like in the figure in the left, and loaded by the torques of the magnitude 1.13 kilonewton meter. Find the maximum shear stress in the steel core and shear stress in the aluminum, and then find the twist angle, the total twist angle of the composite, so of the two metals. So you'll see illustrations on how the cross section will be. This circle here. So this will be the steel. This is the aluminum shell. Okay. It has some dimensions, notably in diameter. Okay, the diameter. So we'll see the. If you remember, we need to take the inside diameter and outside diameter to find the computations. Now we can directly write. First, we can write that this shear stress is G rho and then D dx, like that, right? So both for steel and both and aluminums, they both have the same structure formula for the stress. But let me write. This is for steel. So steel, and for aluminum. And let me write that for steel, this is the rho is from and for the aluminum, it's in between this distance. Now torsion, we know that, right? And then we can input all this inside the torsion formula. So we can write G S and we can separate between steel and aluminum. And we get the torsion. And we know that this will be the inertia, right? The inertia for steel. This is the inertia for aluminum. So first we can take the equations to find the twist rate. So the T is 1.13 kilonewton based on what we have. And then G is steel is 76 GPa, so 76,000 MPa or Newton over millimeter squared. Maybe this is the kilo. I will write in a thousand to make this is Newton. And then multiply. I think to make it a little bit longer. So multiply the inertia. The inertia is pi over 2 for the steel, the inside. And then multiply with 12.5 with power of 4. and then plus. This is pi over 2, 25 millimeter, power of 4, minus 12.5 millimeter, what, power of 4, and then, okay. The result should be in the radian over millimeter. Okay, plus, let me check. It will be equal to the twist rate Okay, now we get this, and then we are going to see back into the each stress for aluminum and steel. We put the twist rate inside, okay, and find the stress. So right here, so for steel, it's the 76,000 MPa. Multiply with the rho at 12.5 millimeter. And then multiply with the twist rate. So this will be fifty-six point 43 MPa. That's for the steel. And then for aluminum, this will be 25 millimeter, and then 5.94. This is 41.58 MPa. Okay, now the second question is asking the total twist. which means the total twist is, so we know the twist rate, okay, we know the twist rate. So we can say that the angle is equal to the integration from 0 to L of the twist rate, dx, right? Or we can say we just integrate dx and it's become L. So this is just a multiplication of this L. So this will be 5.94 multiply with 1.27 meter. Zero point 0.075 radian. That is the total twist, which means all the length, okay, within the length. And of course, if we see from the result, the aluminum, the stress is 41, steel is 56, and I think that is pretty reasonable because steel practically has a higher strength than aluminum, right? Okay. And practically to find the twist, the total twist, we are going to integrate this twist rate with respect to the x. And because the twist rate itself is constant, so we are just taking the integrations of the dx, which is this L, okay, or we can say x, and then substitute with L. So we have the twist rate multiplied by L. Okay, for summary, okay, for this part, let me write here for the linear elastic. So summary. Of torsion for homogeneous linearly elastic bars. So if we see this picture, we have the concentrated torque, and then we have the distributed torque. We have also vary in radius with distributed torque and concentrated torque. Okay. Now, for the cylindrical torsion members whose radius varies, we can write the shear stress as we see it varies in length and also in radius, rho. We can take the torsion as a function of x, multiply with rho, divide with the inertia, and also that is depends on the variable x, and then we take the maximum shear stress as the T max multiplied with R divided by the inertia. So this is for the torsion. This is this max shear stress. And then for the twist, we can write the integration from 0 to L. This is for torque, twist, torque twist equation. Where the theta or the phi here, this is equal to the differences between these two values. So this is the total angle or total twist angle. And if we want to know, if we want to take another approach, a function in between L and 0, if you remember, we can take a dummy variable and write with a function of x. So this will be initial value plus and then let's say we have the dummy variable v to help integrating the value. Dummy variable means it's actually meaningless, but it's helping you to compute the calculus part. Okay? You remember the fundamental theorem of calculus, so this is one way to see. Or you remember we have the arc length in calculus and we have the arc length functions. Then this is how we take the supposedly a value, but we want to make it as a function. So we need to take this into another variable, and we need to change the x inside here with another one to help calculate. Where Where's the picture? Oh, here's the picture. And this is a typical uniform torsion member. So let me rewrite here that the twist angle, as we write on the left side, let me write again with a more simplified, T dx over G and then inertia. So for torsion member that is uniform, with the torsion is constant, then we can write T L G and inertia. And we now have the torque twist equations. So this is the summary. So finally, when the form of the member or the torsion member is uniform and the torque is constant, we can rewrite the formula just this formula. Twist angle equals TL over G and inertia. Okay. So I think this is the more practical way to see the application of finding the twist angle. So at least two formula, the shear stress here, and then this twist angle. That's I think the more practical approach for distortion. And mostly, if you see, like in the exercise, mostly we are dealing with this shear stress, the maximum shear stress, and twist angle. These two. The other part is more of concept. If you are given a set of data or set of functions that you need to be approached with some sort of elements or analytical elements, and you can take all this concept here. Okay. I think it's supposed to be the same. Okay, I think one more example and maybe I think one more example and then we can end the lecture. Okay, it's one more example here. Okay, quite long, quite long here. So a tubular shaft of length L has an outer radius R1, maybe make it bigger, and inner radius R1 over 2. It's made of material with shear modulus G, so it doesn't give you the number, but it's a constant. It is subjected to the n torque of magnitude T0, okay, as shown in figure 1A. This is A here, T0 here. Determine the expression for the tau max, the shear stress maximum for the shaft. Determine the expression for the twist angle, and if the same torque is applied to the solid circular, so you have now different case in B. This is solid circular, producing the same maximum shear stress as in the tubular shaft. What is the radius R2 of the solid shaft? What is the ratio? The last question, what is the ratio of the weight? Okay. The weight W2 of the solid to the weight W1 of the tubular shaft. Okay. So this is basically, we are going to input all the terms inside these questions. We are going to involving all the terms and then using the formula that we've just derived. Okay. So first thing, the expression for the shear stress maximum, the tau max is the T max and then rho over the inertia, right? Okay, let me write the inertia first. The inertia for the tubular shaft is pi over 2 outside minus inside with power of 4. Okay, outside is R1 and inside the inner radius is R1 over 2. So R1 over 2 with power of 4. Okay, so this will be R1 4, 16. This is 16 over 16 R1 power of 4. So this is 15 over 16. So this will be 15 over 32, right? 15 over 32 R1 power of 4. Oh, pi. Sorry, pi. Forget pi. Okay, that's the inertia. So this is inertia. So the tau max is, the T max is the T0 from the given informations. The radius is R1 divided by 15 over 32 pi R1 with power of 4. So we can cancel this out. This will be 32 over 15 T0 over pi R1 cube. Okay, that's the first question. So that's for A. And then for B, the twist angle for, or let me write that this is tau for 1, this is twist for 1, which means the material number 1. Okay, so twist angle is T0 L G and then the inertia. Okay, and let me write inertia of 1. Okay, because we are going to see inertia of the 2, the material 2. So this will be, the inertia is 15 over 32. Let me write directly inside. So 32 over 15. And this will be T0 L and then pi G and then R 1 power of 4. Okay. That's it. And then the C, let me write C on the right. C determine R2, right? Such that we imagine that the tau is equal. So the tau max for one equal for tau max for the second material, which is, we also have same maximum, okay. So we are going to have the T2 equal T1 equal the T0. So developing the tau max for the second material is equal the T T0 R2 over the inertia for the second material. Now the inertia for the second material, let me write here, is just pi over 2 and then R2 with power of 4. Okay, so we can include that inside the equations here. So this will be T0 R2. This will be pi over 2 R2 with power of 4. We can erase this and write down that this will be two T0 over pi R2 cubed. Okay, and we now equaling the first material and the second material. Okay, so the first material, so we get the tau max 1 equal tau max 2. So this will be 32 T0 over 15 pi R1 cubed equal 2 T0 over pi R2 cubed. So we get cancel. This will be 16. So R2 is 15 over 16 with power of 1 over 3. Or R1, sorry, R1. Or R2, if we compute, it's 0.9787 R1. Okay, so that's the ratio, and using this ratio, using the ratio of this radius, we get the weight. We will get the weight 2 over weight 1 is equal A2L. The tube formulations is equal to A1L1, or so the second we can write this, and for this hollow tube we can write pi R2 squared minus R1 over 2 squared L, and this will be 4 over 3, so this will be cancel out, So exchange all with the R1 or R2, and we get this ratio. That is equal to, so R2 change to R1. So 0.979 squared so this will be equal to 1.277. Oh, this is 1, sorry. Okay, I think that's it for today's class. Okay, any questions? No? Tired? Okay. Okay, don't forget midterm next week, okay?